Mrs. Stevenson, units of hc and photon energy. Whenever you're required to figure out the energy of a photon, only knowing a certain wavelength, the following equation can be used. The energy is equal to h, which represents Planck's constant, times the frequency. However, sometimes the frequency isn't known, and you might only know the wavelength. In order to be able to solve for the energy just knowing the wavelength, you have to remember that frequency is also represented by the speed of light, which is represented by c, divided by lambda. This symbol lambda represents the wavelength. So if we take c divided by lambda and plug this in for our frequency in our energy equation, we get an equation that looks like energy is equal to hc, or Planck's constant, times the speed of light, divided by the wavelength, or lambda. Both Planck's constant and the speed of light are constants. They don't change. They always will have the same value. So we can actually put in the numerical value for each of these constants and simplify this equation. So if we plug in our numerical values, we have energy equaling Planck's constant is 6.626 times 10 to the minus 34 joules, minus 34 joules per hertz. And then we multiply that by the speed of light, which is 2.998 times 10 to the 8th meters per second. And we would still have to divide by the wavelength lambda. However, when we're working with hc and we have Planck's constant in terms of joules, it's just not a convenient unit to use. We want to convert all of this into electron volts so that the number doesn't end up looking really, really small. So to convert our hc numbers and our joules and meters per second into electron volts, we are going to start off with our Planck's constant, 6.626 times 10 to the minus 34 joule hertz, and then still multiplying by the speed of light, 2.998 times 10 to the 8th meters per second. But we're also going to use the conversion that 1 electron volt is represented by 1.602 times 10 to the minus 19, minus 19 joules, and that 1 meter for our meters per second is represented by 10 to the 9th nanometers. We have to convert our meters into nanometers because most wavelengths are given in nanometers. So if we multiply all of this through, we find that hc can be more conveniently represented by 1,240 electron volt nanometers. This is a lot easier to put into an equation than all of this. So if we go back to our original energy equation, which was hc divided by lambda, or the wavelength, we can now plug in this numerical value in for hc, so that we say that the energy of a photon can be represented by 1,240 electron volt nanometers, all divided by the wavelength.